Hello. Today we're going to be talking about an important theorem that we will be using to help us prove whether or not two triangles are congruent, and that's the side angle side congruence theorem. Side angle side is kind of a mouthful, and so sometimes instead of calling it side angle side, we will call it SAS. So side angle side or SAS are the same thing. In order to use side angle side, notice that the angle is listed in between two sides. So you have to have two corresponding congruent sides and the angle that's included or sandwiched in between those sides. So the included angle is the angle that is marked here. Angle A is the included angle between AB and AC. Angle D is the included angle between DE and DF. So if we have two sets of congruent sides and the angle included between those congruent sides are congruent, then the two triangles themselves are congruent. So first, let's practice finding that included angle. So for number 3, these are kind of numbered weird, but we'll just give it a whirl. Don't worry about the numbering. They have sides JK, which is right here, and KL, which is right here. I'm doing my best to trace these, but it's a little funky. So then what is the included angle between those two sides? It would be this angle that's right here. So we would call that angle JKL. We do need to use all 3 letters there because there's more than one angle happening at K. Or you could say angle, we can just switch the order to LKJ. Either of those are perfectly correct answers. Let's try another one. So I'm going to get rid of those markings so we can look at things a little clearer. We want the included angle between sides LP and LK. So these two pink sides. What is the included angle? The included angle is this angle right here. And so we're going to name that with our 3-letter name. We can either call that PLK, or if you'd rather name it the other way, just go in the opposite order, KLP. Those both mean the same thing. Let's try one more. So I'm going to get rid of this chicken scratch here. We have side KL and side JL, which is this one. What is the included angle? The included angle is this angle right here. So angle JLK. Remember the vertex is always in the middle. Or if you'd rather, we could call that angle KLJ. They mean the same thing. So those are just what your included angles are. Important to know which one is the included angle, because if you don't know which one is the included angle, using this theorem is pretty difficult. The next thing we're going to do is look at some triangles here and see if, based off of only the things that are marked in the diagrams, do we have enough information to say they are congruent by using our side angle side property, or theorem. So let's take a look at number 9. With most of these, we have two triangles smashed up against each other. It might make things easier to see if you kind of pull the triangles apart. I'll show you in a second. So triangle ABD, so if I pull that off to the side here, not going to be the best picture, but enough for us to get the idea. And triangle CDB, which would be the bottom one. Now let's label what we know. We know that AD is congruent to BC. We know that angle ABD is congruent to angle BDC. Okay, what else do we know? Well, notice that BD is part of both triangles. So since BD is part of both triangles, it's going to be congruent to itself by the reflexive property. So, can we use side angle side? I have two congruent sides. I have one congruent set of angles, but is that angle included in between the two congruent sides? The angle is not the included angle, so this one is no. We cannot use side angle side to say these two angles are congruent because this is not an included angle for the two congruent sides. Let's try another one. So again, we can pull these apart. We have triangle YXZ. So that would be the one that's on the right. And we have triangle WXZ, or the one that's on the left. Let's fill in what they have marked. They have marked this is a right angle, They have marked that WX is congruent to ZY. And what else can we say just by looking at the picture? Two things. Because ZX or XZ is part of both triangles, that's going to be congruent because the same side is congruent to itself. And then let's see what else we can say. We can say that this angle right here, WXZ, is also a right angle because this right angle here and WXZ are a linear pair, and 180 minus 90 equals 90, or 90 plus 90 is 180. These are linear pairs, so they have to be supplementary. Since this one's 90, this one's also 90. So now let's carefully look, can we use side angle side? It looks okay with triangle WXZ because I have my two sides that are congruent to the sides in the other triangle, and angle X here is a congruent angle, or a 90-degree angle, and it's the included angle. However, in the other triangle, this is not the included angle. The included angle would be the angle up at Z there. So this one is no, because not the included angle. Similar rationale to the first one of those we did. All right, one more like this. I'm going to scoot my screen here. We have triangle EFH, which is the one that's off to the right here. And we have triangle FG or GHF, which is the one that's off to the left. Let's fill in what we know. We know that FE is congruent to GH. And we know that the angle here, FHG, is congruent to the angle here, FEH. What else do we know? Well, since FH is part of both triangles, by the reflexive property, it's going to be congruent to itself. So now let's look carefully. We have our two sides are marked as congruent. The angle that's marked as congruent is sandwiched in between them, so it is the included angle. So this is a perfect scenario of yes. We can use side angle side here because we have two congruent sides and their congruent angle included. That is it for using the side angle side property. So basically, let's just look back at the theorem. Make sure you're always dealing with two sets of congruent sides and a congruent included angle. If the angle is not included, we cannot use this theorem. That is it for today. Have a wonderful day.